we're now going to start looking at a class of groups known as permutation groups, which are built up out of bijections of a set. So let's look at this. Definition 47 is that a permutation of a group A, of a set A, we don't want A to be restricted to being a group, is simply a bijection, alpha, from A to A. The idea is that alpha here permutes the elements of A. It sends every element of A to some other one, sort of mixes them all up. A set of permutations of a set A forming a group under composition is called a permutation group. Now, one of our standard examples that we've seen in this course is a permutation group under this definition. So, for example, we've looked at this several times now. Let's let G be the set of all functions from the unit interval to itself, where f is a bijection. So because f here is a bijection, it satisfies the definition of 47, and it is a permutation of the interval from 0 to 1. And then this set G that we've looked at several times is a group that is formed of bijections of the interval 0, 1. So this is an example of a permutation group, but we're going to be primarily interested in permutation groups of finite sets. As it turns out, those are a little bit easier to get your hands on, and we're going to have specific ways that we write down the elements of permutation groups on finite sets, and they turn out to be very important to the study of algebra in general. So, as I say, we often consider permutation groups of finite sets. In particular, we let Sn be the set of permutations on the set of numbers 1, 2, 3, up to n. It's the permutations on a set with n elements. Now, as it turns out, the fact that these elements are numbers is not particularly important. The only thing that matters to the permutation groups is that we've got n distinct objects that we're working with, and not what those actually are. So we usually use numbers because they're easy to write down and keep track of. So let's look at, for instance, the set S5. This is the set of bijections of the set 1, 2, 3, 4, 5. And in fact, S5 is a group under composition, and it's called the symmetric group. On 5 elements. A particular element of S5 might be the following. So let's consider the following alpha belonging to S5. And alpha is just a function, and it's going to take the various elements of S5 to various other elements of S5, and all we have to make sure of is that alpha winds up being a bijection. So we could take alpha of 1 to be 2, alpha of 2 to be 5, alpha of 3 to be 3, alpha of 4 to be 1, and alpha of 5 to be 2. And that's an element of S5, the symmetric group on 5 elements. It's simply a bijection going from the set 1, 2, 3, 4, 5 back to itself. Now, of course, this is a pretty big way of writing this. It takes up a lot of space, and so we've got a couple of more compact ways that we're going to describe these permutations when we're talking about finite sets. So we can write this more compactly. And the way that we do that is we're going to take a grid here, and along the top we're going to write down all of the elements of our set, of our 5-element set, and then the notation here essentially puts the inputs to the function in the top row and the outputs to the section in the bottom row. So the alpha that we had before has an input of 1 and an output of 2, an input of 2 and an output of 5, an input of 3 and an output of 3, an input of 4, output of 1, and an input of 5, an output of 4. So this is a more compact way of writing down the permutation alpha, simply by listing all the inputs along the top and all the outputs along the bottom. This allows us to compute the product of two permutations easily. Now, by product, I really mean composition here. The operation on the symmetric groups is composition. So if I look at another permutation, beta, it's going to have the same set of inputs, but it's going to have the outputs 3, 1, 5, 2, 4. Then I can find alpha, beta using this notation. We'll do a couple of these, figure out a couple of these inputs and outputs explicitly, and then we'll see what the result is, or how to compute this more efficiently. Now, of course, the composition of two bijections is another bijection, or in other words, the composition of two permutations is a permutation. So let's look and see what the composition evaluated at 1 should be. Well, it's going to be alpha of beta of 1. Now, beta of 1 we can read from the notation on beta, and we see that beta of 1 is 3. So then we get alpha of 3, and alpha of 3 we see is 3. So that means that in our product, alpha times beta, alpha beta of 1 is equal to 3. Similarly, we can calculate alpha of beta of 2. Now, beta of 2 is equal to 1, and then alpha of 1 is equal to 2. So in the product of these two permutations, 2 gets sent to 2. So what we can see is that we can really just use the notation that we've got above with the two grids in order to compute these. So if we want to know what happens to 3, first of all, we're moving from right to left, just like we do with ordinary composition of functions. And so we see that in beta, 3 goes to 5. But then in alpha, 5 goes to 4. So that means that in the product, 3 will go to 4. A good way of thinking about this is that we're applying the two permutations in sequence. We're applying beta first, and then we're applying alpha. And so if we throw 3 into this, first we apply beta, which sends 3 to 5, and then we apply alpha, which sends 5 to 4, and so all together, 3 gets sent to 4 when you apply both of them. And we can continue this. 4 gets sent to 2 under beta, and then 2 gets sent to 5 under alpha. So 4 gets sent to 5 in the product. And then 5 gets sent to 4, and 4 gets sent to 1 in the product. So 5 gets sent to 1. So this allows us to compute the products of these of two permutations fairly easily. Now let's try multiplying these two permutations in the other order. Let's take beta times alpha. So beta goes 3, 1, 5, 2, 4. Alpha goes 2, 5, 3, 1, 4. And so, starting with 1, we see that in alpha, 1 goes to 2, and in beta, 2 goes to 1. So in their product, 1 will go to 1. In alpha, 2 goes to 5, and then 5 goes to 4. In alpha, 3 goes to 3, and then in beta, 3 goes to 5. In alpha, 4 goes to 1. In beta, 1 goes to 3. And then in alpha, 5 goes to 4. And in beta, 4 goes to 2. So the product of beta times alpha is this second product that we've got down on the lower right. That sends 1s to 1, 2 to 4, 3 to 5, 4 to 3, and 5 to 2. In particular, you'll note that these two results that we get are not the same. Alpha times beta and beta times alpha are very different from one another. And in general, this is going to be the case. Symmetric groups are highly non-abelian. That's just because composition of functions is not commutative. However, there are some relations that we can use to understand the structure of these. So let's look at a smaller example than S5. Let's look at S3. So S3, which is permutations of the set 1, 2, 3. And let me go ahead and write them down. The identity element for these groups, in fact, for all of these groups, is going to be the bijection, which just takes every element to itself, the identity function. And for S3, we can write that identity function this way, 1 to 1, 2 to 2, 3 to 3. Let me go ahead and call alpha the permutation which takes 1 to 2, 2 to 3, and 3 to 1. And let me take beta to be the permutation that takes 1 to 1, 2 to 3, and 3 to 2. Excuse me. And now we can get some more. alpha squared is what we get when we multiply alpha by alpha. So if we multiply alpha by alpha, the first alpha sends 1 to 2, the second alpha sends 2 to 3. The first alpha sends 2 to 3, the second sends 3 to 1. And then for the last, the first alpha sends 3 to 1, the second alpha sends 1 to 2. So we get alpha squared there. And then we've got a few others. I'm just going to go ahead and write these down. Alpha times beta is a permutation that sends 1 to 2, 2 to 1, and 3 to 3. Alpha squared times beta sends 1 to 3, 2 to 2, and 3 to 1. And in fact, this is it. These are the only permutations in S3. There are only 6 different ways of rearranging 3 elements, basically. So here are all of the elements of S3. However, let's check out the product beta times alpha. You notice that beta times alpha doesn't show up in our list here. We've got E alpha, alpha squared, beta, alpha squared, beta. And so there are lots of products of these things that we haven't listed out. However, because S3 only has 6 elements, the product beta times alpha must be one of these 6 elements. So let's compute it. Beta times alpha is 1, 2, 3, 1, 3, 2 times 1, 2, 3, 2, 3, 1. So alpha sends 1 to 2, beta sends 2 to 3. Alpha sends 2 to 3, beta sends 3 to 2. Alpha sends 3 to 1, then beta sends 1 to 1. So we're left with this, which, notice, is the same as alpha squared times beta. Furthermore, let's check out beta squared. So beta squared, 1 goes to 1, then 1 goes to 1, so 1 continues to go to 1. Now in the first beta, 2 goes to 3, and in the second, 3 goes to 2. So we get that 2 goes to 3, and then 3 goes to 2. And then for the last one, the right-hand beta sends 3 to 2, and then the left-hand beta sends 2 to 3. So we in fact get the identity out of it. Beta squared is the identity. Similarly, it turns out that alpha cubed is also the identity. And so there are these various relations between the elements of S3 that we can use to simplify expressions involving them. In fact, using these 3 relations, the relation that beta alpha equals alpha squared beta, the relation that beta squared is the identity, and the relation that alpha cubed is the identity, we're able to simplify any product of elements in S3 down to one of the 6 expressions that we started with. So for instance, if we want to know what beta times alpha squared is, well, we could write that as beta alpha times alpha. And we know that beta alpha is alpha squared beta. But we could do that again. We can use associativity to look at beta alpha here. Beta times alpha is another alpha squared beta. So we get alpha to the 4th beta. But of course, alpha cubed is the identity, which means that 3 of these alphas don't matter. And in fact, we just get alpha beta back. So the permutation groups tend to have lots of relations like this that allow you to simplify equations and write everything in terms of a simple set of standard expressions such as these ones. So we see here that there are 6 elements of S3. Let's think about how many elements there are for Sn with any n. So let's ask the question, how many elements are in Sn? Or in other words, what's the order of Sn as a group? So every element of Sn can be written as an expression of the following form: 1, 2, 3, up to n. And then some elements down below, I'll call them A1, A2, A3, up through AN, where the A1 through AN are the numbers 1, 2, 3, up to n in some order. We can write down every element of Sn in this way. So let's think about how many ways there are for us to actually write that down. Well, we can think about how many ways there are of choosing A1 if we were to actually build ourselves a permutation this way. And we can see that there are n ways to choose A1. We could choose any of the numbers from 1 to n. So there are n ways to choose A1. And then, how many ways are there to choose A2? Well, we could choose any number from 1 to n except what we already chose for A1. So if we chose a 5 here for A1, we can't choose a 5 here for A2. That wouldn't be a bijection. That function would take 1 to 5 and 2 to 5, which doesn't work. So the numbers A1 through AN all have to be distinct. And so in particular, there are n-1 ways to choose A2. There are n-2 ways to choose A3, because we could choose any of the numbers from 1 to n except for what we chose for A1 and A2. And continuing down here, there are going to be 2 ways to choose an-1, and then once we get to the last number, the an at the end, there's only going to be one option left. We'll have already chosen n-1 of the numbers from 1 to n, and so there'll only be one left. There will only be one choice for an, so there'll be one way to choose an. So to find the total number of ways to make all of these choices, we multiply all the different options we have at every point together. So this means that the order of Sn is going to be n times n-1 times n-2, down, times 2 times 1, or, in other words, n factorial. So the order of the symmetric group on n elements is n factorial. So this means that the order of S3 that we looked at before is 3 times 2 times 1, which is 6, which justifies what I was saying before. And then the order of S5 that we were looking at earlier is 5 times 4 times 3 times 2 times 1, which is 120. So as we can see, the order of the symmetric groups increases quite quickly as the size of the group they're operating on increases. The order of S6 is 720, And the order of S7 is 7 times 720, which I believe is 5040. It just goes up and up and up really fast. The order of S10 is a ridiculously large number, and things just keep going. So this gives us some insight into the structure of Sn, how big they can get, and they do get very big. And because of that, we actually want an even better notation. The notation that we've used up till this point has been quite useful for understanding things like how many elements of Sn there are, and of making sure we understand how to compose two permutations. However, we do in fact want an even better notation, which is going to be called cycle notation. And it's going to be more compact, but we need to think a little bit more when we use it. It's not going to be quite as explicit and direct as the notation that we were using before, although it's still going to be unambiguous as long as we interpret it correctly. So let's look at cycle notation. So here's the idea. In a permutation, alpha, we have that alpha of 1 is something, or let me write it this way. 1 gets sent to some number under alpha. 1 gets sent to alpha of 1. But then that number alpha of 1 also has to get sent somewhere. So alpha of 1 also gets sent to alpha of 1. Alpha of 1 is some number in your set, which gets sent to alpha of 1. And so we can basically ask what happens when I apply alpha over and over and over again to some number in my original set. Now, if we're starting with a finite set, then this sequence of numbers has to eventually repeat. And it turns out that when that happens, it will have to eventually come back around to 1. And so the cycle notation takes advantage of this fact when we're looking at permutations on finite sets in order to more efficiently write down a permutation. So let's consider the beta permutation we had before that sits in S5. 31524. So let's look at what happens when we follow a chain of applications of beta. What happens when we apply beta a bunch of times? So when you apply beta to 1, you get 3. And if we apply beta to 3, we get 5. And if we apply beta to 5, we get 4. And if we apply beta to 4, we get 2. And if we apply beta to 2, we get 1. And this right here captures all of the information about beta. It tells you where everything goes. Everything in our set from 1 to 5 shows up somewhere in this beta. So we can see here, if I want to know, where does beta send 5? I just have to find where 5 appears in this sequence and see what the next number is. And so this is the sort of idea that we want to encode. Now we want to do this a little bit more efficiently here. We're going to encode this in the following way. We're going to open up a parenthesis and we're going to write down the sequence 1, 3, 5, 4, 2, and close parenthesis. And what this notation means, to say that beta equals this, means that beta sends 1 to 3, sends 3 to 5, sends 5 to 4, sends 4 to 2. Every number gets sent to the next number in this sequence, and then 2 gets sent back to 1. This is called the cycle notation for the permutation beta. And we can do this with lots of permutations, though there are some issues that can come up, which we're about to look at. So cycle notation provides an efficient way of writing down a permutation. We can now write down the permutation using just 5 numbers and a couple of parentheses, as opposed to the 10 numbers in 2 rows with 2 big parentheses that we had before. So let's look at some other examples and see how things can be different. So let's look at I don't want to look at alpha yet. I want to look at gamma, which is the permutation 1 to 4, 2 to 3, 3 to 2, 4 to 5, and 5 to 1. So let's write down what gamma is using our cycle notation. Now, really, we can start with any element here. But it's traditional to start with the smallest element that hasn't been used yet. So if I want to encode this permutation gamma using cycle notation, I'll start with 1 here. And I'll say, all right, well, there's 1. Well, then where does 1 go under gamma? 1 gets sent to 4. All right, where does 4 go to under gamma? 4 goes to 5. 5 then gets sent to 1. And because 5 gets sent to 1, and 1's what we started with, we close the parenthesis here. Now, you'll notice that we haven't described what happens to all of the various elements of gamma. We looked at what happened to 1 when you applied gamma repeatedly, and if you start with 1, you get sent to 4, then 4 gets sent to 5, then 5 gets sent back to 1, and you're going to continue on this cycle over and over and over again. But we haven't talked about what happens to 2 or 3. Sometimes a permutation will require multiple cycles to describe. So when that happens, when you haven't actually written down all of the elements in the underlying set, we need to start with another one. So at this point, we say, all right, we've described what happens to 1, 4, and 5 under gamma. So what's the smallest number we haven't described? And that's 2. So we'll start our next cycle with 2, and we say, all right, well, where does 2 get sent? 2 gets sent to 3. And 3 gets sent back to 2. So we can close the parenthesis there. So that means that this gamma has to be written using 2 cycles, which is not a problem. Many permutations we work with have to be written using multiple cycles, and that's how we can do it. So then let's look at another example. Let's look at alpha from before. This is the permutation that sends 1 to 2, 2 to 5, 3 to 3, 4 to 1, and 5 to 4. Let's try to write alpha in cycle notation. We'll start with 1 as normal. 1 gets sent to 2, 2 gets sent to 5, 5 gets sent to 4, 4 gets sent to 1. All right, so that's handled everything except 3. We've described what happens to every element of the underlying set except 3. So let's start a new one there. And we see 3 gets sent to 3. 3 gets sent back to itself. So we can write that cycle this way. Now, typically, we don't write these. Typically, we don't write cycles of length 1, meaning cycles with only one element in them. So, it's not wrong to write the cycles of length 1, but almost always we would write this alpha as just the cycle 1, 2, 5, 4, and then implicit in this notation is that anything that's not written in a cycle just gets sent back to itself. That alpha just sends one of these elements to itself. Any one of those elements to itself. Now, the exception to this is the identity permutation, which just sends everything to itself. We usually write that in cycle notation as just a single cycle of length 1. Because we do want to give it some sort of notation in cycle notation. Okay, so this is how we can write down permutations using cycle notation. We can also look at multiplying cycles together using cycle notation. So let's look at that. Let's let delta be the permutation that we get when multiplying the permutations defined by these cycles together. 1, 4, 2, 3, 2, 1, 5, 2, 1, 3, and 4, 5. And we want to multiply, or we want to express delta in a better way. In a moment, we'll have a definition for what we mean by better way. But for the moment, I want to try and figure out, all right, well, how can we express delta using as few cycles as possible? We can actually go through things in a very similar way to how we did it before, where we start with a 1 here and we ask, all right, well, where does 1 get sent under delta? And the point to remember is that we multiply cycles, just like permutations, right to left. And trace where 1 gets sent under each cycle. So for instance, if we want to know where 1 gets sent, what we're going to do is we're going to trace its path as it gets worked on by each one of these cycles in sequence from right to left. So for instance, the cycle 4, 5 doesn't affect 1. So 1 just gets sent to 1 there. But then we apply the cycle 5, 2, 1, 3. And under this cycle, 1 gets sent to 3. And now we look at the next cycle. The next cycle is 2, 1. And 3 does not get sent anywhere under 2, 1. 1 would have, but we're not 1 anymore. When we throw 1 into this delta permutation, Well, then 1 got sent to 3 under the second cycle in the sequence, and 3 doesn't get changed when you apply 2-1, the cycle 2-1 to it. Now 3 under the leftmost cycle gets sent to 1 because the last element in the cycle goes back to the first. So what we see is that under delta, when we apply all 4 of these cycles, all 4 of these permutations that multiply to make delta, 1 gets sent back to 1. All right, so that gives us our first cycle. Now let's look at what happens to 2. So 2 maps to 2 under 4, 5. It maps to 1 under 5, 2, 1, 3, which maps back to 2 under the cycle 2, 1, which maps to 3 under the cycle 1, 4, 2, 3. And now we're going to see what happens to 3. We're going to continue this cycle here. 2 went to 3, so then we'll see what 3 goes to. 3 goes to 3 under 4, 5. 3 goes to 5 under the cycle 5, 2, 1, 3. 5 doesn't change under 2, 1, and 5 doesn't change under 1, 4, 2, 3. So that means 3 gets sent to 5 in delta. So let's see where 5 gets sent. Well, 5 gets sent to 4 under the first cycle. 4 doesn't change under the second cycle or under the third cycle, but under the fourth cycle, 4 gets sent to 2. And that means that in delta, 5 gets sent to 2 when you apply everything together, which means that we've finished this cycle here. Now, we want to see where 4 goes. Now, we can make an argument here that 4 will have to go to 4 because there's nowhere else for it to go. Notice that delta only includes numbers from 1 to 5, which means that it's a permutation on 5 elements. We've already seen where 4 of those elements go. We know that 1 goes to 1, 2 goes to 3, 3 goes to 5, and 5 goes to 2, which means that the only thing left for 4 to go to is 4. Delta must send 4 to 4. But we can also check our work here to make sure. So let's see, 4 goes to 5 under the first cycle, then 5 goes to 2 under the second cycle, 2 goes to 1 under the third, and then 1 goes to 4. So that works out. And of course, we usually don't write the single element cycles, and so this whole expression, the product of a bunch of cycles here, can be simplified down to just 2, 3, 5. So the cycle way of expressing permutations can be used to multiply permutations together. And it's an efficient way of doing so in terms of space on the page. It does take some getting used to in order to do it efficiently. Eventually, with some practice, you will get to the point that you don't need to write down chains like this. But when you're first starting off, I recommend doing so because it helps to understand what's really going on. All right, now one of the things that we've done both previously when we were turning our alpha, beta, gamma into an expression involving cycles, and here where we're taking a bunch of these cycles and multiplying them together to get delta, what we are really doing is showing that we can write any permutation as a product of cycles, but more than just a product of cycles, as a product of cycles that have no terms in common. So, first of all, note that we call two cycles are disjoint if they have no elements in common. And it turns out disjoint cycles are very important to us for a few reasons. The first one is given to us by Theorem 48, which says that every permutation can be written as a product of disjoint cycles. Every permutation I should specify of a finite set. Really, all of our results that we're going to be talking about here only really hold true for finite sets. Cycles aren't really useful when talking about permutations of infinite sets. But Theorem 48 is that every permutation can be written as a product of disjoint cycles. The proof is basically what we've already gone through. The proof is basically using the construction that we did at the beginning when we were turning the alpha, beta, and gamma permutations into cycles. And all of those cycle descriptions were a product of disjoint cycles. So the next thing that we want to see about disjoint cycles is that they commute. Now normally, as we've seen, two different permutations typically won't commute. However, if the two permutations we're looking at are disjoint cycles, then they will. So Theorem 49, disjoint cycles commute. And I want to go through this to show some of the notation and ways that we work with cycles in general when working on proofs in order to make them better to work with. So as a proof, let's let alpha be, and of course we don't know anything about the cycles we're looking at except that we want them to be disjoint. In particular, we don't know how big they're going to be. They're not going to be the same size, or they may not be the same size. So we can just write down our cycles like this. Let alpha be the cycle A1 to AM, beta be the cycle B1 to Bn, and we want these to be disjoint cycles. And we want to show that alpha beta is equal to beta alpha. Now, one way of doing this would be to show that they have the same description in terms of the big grid that we had before, but that's really sort of unwieldy. Remember that even though we're writing down alpha and beta in terms of these cycles or these grids, at the end of the day, they are still functions. They're bijections. And to show that two functions are equal, the thing to do is to show that they are equal on every one of their inputs. Show that no matter what you plug into either of these two functions, we get the same result out of it. So we want to show that alpha beta is equal to beta alpha, i.e. that alpha beta of x is equal to beta alpha of x for all x. So let's let's see what we get. So let's let x be any element. If x is equal to ai for some I, then let's look at what we get. Then alpha of beta of x will be alpha of beta of ai. Now, ai does not appear in beta. And this is because we assumed that alpha and beta were disjoint cycles, which means all the a's are different than all of the b's. None of the a's appear in the b's, none of the b's appear in the a's. So in particular, this means that beta of ai is just going to be ai, because ai doesn't appear in the cycle beta, and any element that doesn't appear in the description of beta is assumed to just be sent to itself under beta. So beta sends ai to ai. And then alpha of ai is ai plus 1. So this is another piece of notation that winds up being very useful to us. So the alpha here, if I look at where ai is in the sequence, then ai plus 1 comes right after it, which means if we apply alpha to ai, we get ai plus 1. Now here we interpret am plus 1 as am, or as not as am, but as a1. So notice that am plus 1 isn't actually defined in our cycle, but if I apply alpha to am, then I will get a1 because that's how the cycle notation works. It sends the thing at the end of the cycle back to the beginning. Okay, and we have that. We can now look at what happens when we take beta alpha of x. Still under the assumption that x is ai for some I. Now beta of alpha of ai, alpha of ai is ai plus 1. Now beta of ai plus 1, once again, ai plus 1 is one of the a's, is one of the elements in the cycle description for alpha, and in particular that means that it isn't one of the b's. So since ai plus 1 isn't one of the b's, that means that beta of ai plus 1 is just ai plus 1. Beta doesn't actually change it at all. So we get that if x is equal to ai for some I, then alpha beta of x is equal to beta alpha of x. And so we get that at least on some possible inputs, the two functions alpha beta and beta alpha are the same. So let's continue. Another possibility is that x could be bi for some I. Whoops, sorry. If x is equal to bi for some I, then a similar thing happens. If we take alpha beta of x, this is alpha of beta of bi. Now, beta sends bi to bi plus 1. And then because the b's don't appear in the cycle description of alpha, alpha sends all the b's to themselves. And so alpha of bi plus 1 is bi plus 1. And similarly, beta alpha of x is beta of alpha of bi. Alpha of bi is just bi. Beta of bi is bi plus 1. So that shows that alpha beta and beta alpha of x give the same result when x is a bi for some I. Now, we are almost done. However, there is a third possibility. We considered the case when x is equal to ai for some I, and we considered the case where x is equal to bi for some I, but it could be the case that the input to our permutation isn't equal to either one of them, isn't equal to an ai and isn't equal to a bi. So if x is not equal to any ai or any bi, then alpha beta of x, which is alpha of beta of x, well, because x is not equal to any of the bi's, beta doesn't do anything to it. So beta just sends x to x, and because x is not equal to any of the ai's, alpha doesn't do anything to it, and so alpha of x is just x. But of course, something almost identical happens when we take the other direction. So alpha of x is just x because x is not an ai. Beta of x is just x because x is not a bi. So what we get is that alpha beta of x is again equal to beta alpha of x. And now we've considered all our possibilities. So x is either equal to an ai, equal to a bi, or equal to none of the ai's or bi's, and we've handled all those cases. So this means that for any x, we have that alpha beta of x is equal to beta alpha of x. But remember that functions are defined by their outputs, or by the pairing of their inputs to outputs. Therefore, if two functions are identical, no matter what input you plug in, then that means that they are in fact the same function. So therefore, alpha beta equals beta alpha. So this is going to be very helpful to us. We now know that disjoint cycles commute, which allows us to manipulate the expressions that we have in useful ways. And in particular, it allows us to sort of give an improvement on the theorem that every permutation can be written as a product of disjoint cycles. So we can also say the following. The expression of a permutation in a finite set as a product of disjoint cycles is unique up to reordering of the cycles. So, for instance, we had that gamma is equal to 1, 4, 5 times 2, 3. Well, this expression of gamma is unique, with the only exception being that we can rewrite the order of the cycles. Also, each cycle can be written in different ways. So, for instance, the cycle 2, 3 can also be written 3, 2. The cycle 1, 4, 5 can be written as the cycle 4, 5, 1. So, within each cycle, there are some different ways of writing it down. And then when a permutation is a product of cycles, you can reorder those cycles. But those are the only things that can be different between two disjoint cycle decompositions of a permutation. Now, one thing that it turns out that we can use this to determine the order of a permutation very easily. So it turns out that we're, based on the next theorem, we're going to be able to tell instantly what the order of this permutation gamma is. So theorem 50 is where we're looking, which says that the order of a permutation of a finite set is the least common multiple of the lengths of the cycles in its disjoint cycle decomposition. So, for instance, the order of gamma that we had before is going to be the order of 2, 3, 1, 4, 5. And according to this theorem, that's going to be the least common multiple of the lengths of the two cycles in the permutation, in its disjoint cycle decomposition. In other words, the least common multiple of 2 and 3, which is 6. And you can check this out yourself. You can take various powers of gamma and raise them to higher and higher powers and see that gamma to the 6th is the first power where you get the identity back. All right, let's see a proof here. Now, one very important step of this proof will be one of your homework exercises, but I'll point that out. All right, so let's let alpha 1, alpha 2, up through alpha n be disjoint cycles. Technically, I should say pairwise disjoint, meaning no two of them have any elements in common. This means that the A1 through AN commute. So since they commute, for any k, a natural number, we have that the kth power of their product is equal to the product of their kth powers. So thus, alpha 1 through alpha n to the k is equal to the identity if and only if alpha I to the k is the identity for all I. And the reason for this is basically that because the alpha i's are disjoint, they sort of can't interact with each other. If alpha 1 to the k is not identity, then there's nothing that any of the other alphas can do. None of the other alphas affect the elements that are manipulated by alpha 1 at all. And so the only way for this product of cycles to be the identity is if each one of the factors is the identity. Again, because they're all disjoint. None of this argument would apply if we weren't looking at disjoint cycles. This means that the order of alpha 1 through alpha n has to be the least common multiple of the order of alpha 1, the order of alpha 2, up through the order of alpha n. Since alpha I to the k equals the identity if and only if the order of alpha I divides k. We looked at this before when we were first talking about order. An element raised to the kth is equal to the identity if and only if the order of that element divides k. So if we want all of these ai to the k's to be the identity for all I, then that means that each one of these k's must be divisible by the order, I'm sorry, there's only one k. It means that k has to be divisible by all of the orders of the ai. And the smallest number that does that is the least common multiple of all of the orders of the alpha i's to begin with. So the only thing that's left is to note that by the homework, the order of alpha I is equal to the length of alpha I as a cycle. In other words, the number of elements in it. So this does take some work, but that's part of your homework. And it turns out that the order of any cycle is just equal to the number of elements in the cycle. So the order of the cycle 1, 4, 5 that we had before is 3. The order of the cycle 2, 3 is 2. And so that gives us the end of the proof here. One of the things that Theorem 50 allows us to do is to count the number of elements that we have in our group of a given order. This is sort of similar to the theorem that we had for cyclic groups. We had a similar theorem for cyclic groups that let us know how many elements there were of a given order within the group. For symmetric groups, these permutation groups, the process is a little bit more complex, not as direct, but we still can use this theorem to do it. So let's take as an example, we can ask how many elements of order 12 are there in S7. So we know now that an element is going to be of order 12 if it's a product of cycles where the least common multiple of all of the lengths of those cycles are 12. So we can think about, all right, well, how many ways are there for us to set that up? And we can try and imagine, all right, well, how can we set up some cycles where we want the least common multiple of the lengths to be 12? And we might have more things here. And this is going to be limited by the number of elements that we have to work with, because we need all of these to be disjoint. So we want to make sure that the least common multiple of all these lengths is 12. And if you play around with this a little bit in this problem, you'll find that there's really only one way of doing that here, and that's to take a cycle of length 3 and a cycle of length 4. Now, if we had more elements to work with, if we were working in S9, there would be more options for this. But in S7, this is the only way of doing it. This is the only way of constructing two cycles where the total number of elements is at most 7, because that's the number we have to work with, and where the least common multiple of those two is 12. So actually, let me write it this way. So the only way for us to get a cycle like this is in this form. One cycle being of the form A1, A2, A3, the other being of the form B1, B2, B3, B4. So next we can ask, all right, this is the form of the elements of order 12. So how many of them do we get? So at this point we can start looking at at how many ways we have to choose, like the A1, A2, A3, etc. So we can say, all right, well, there are going to be 7 ways to choose A1, because there are 7 elements in our group, in our set rather. 6 ways to choose A2, 5 ways to choose A3. So let's focus on the first cycle here. So that means that it looks like we have 7 times 6 times 5 ways to construct A1, A2, A3. But actually we've overcounted here. And the reason is that a cycle has more than one way of being described. So for instance, the cycle 1, 2, 3 is the same as the cycle 2, 3, 1, which is the same as the cycle 3, 1, 2. Each of these describe the permutation that sends 1 to 2, 2 to 3, and 3 to 1. We've just written them in a slightly different order, but they are in fact exactly the same element. We've only written them differently. So in fact, a cycle of length 3 has 3 different places it could start. We could start with, well, A1, A2, or A3 here, basically. And so we don't want to count all 3 of these separately. So we need to divide by 3. So this 3 here is the number of elements we could start the cycle at. Or in other words, this is the length of the cycle. Because we could start the cycle at any point along it. We could start at 1, we could start at 2, we could start at 3. And so we need to divide by 3, because that's the number of times we've counted each cycle. Because if we just multiply 7 times 6 times 5, we've counted every cycle. We've counted these 3 cycles separately, once with 1 in front, once with 2 in front, and once with 3 in front. So that means that there are 7 times 6 times 5 divided by 3 ways to construct the cycle 1, 2, 3, A1, A2, A3, which is 70 ways to construct A1, A2, A3. So now let's use the same sort of logic with B1, B2, B3. So once we've constructed our cycle A1, A2, A3, there are going to be 4 times 3 times 2 times 1 ways to construct B1, B2, B3, B4, because we've already used up 3 of our elements constructing our first cycle. But of course, we need to divide that by 4 so that we don't double count things the same way that we did before. So this gives us a total of 6 ways to construct our 4-element cycle once we've constructed our 3-element cycle. So our answer then is 6 times 70 is 420 elements of order 12. So we don't have a specific theorem the way that we did before, which just gives us a formula to plug in our numbers, and it tells us how many elements of a given order there are within a given symmetric group. But we can figure it out using Theorem 50, which tells us how to calculate the order of a product of disjoint cycles. Okay, so now let's look at another way of describing permutations. We've seen so far that every permutation can be described as a product of disjoint cycles. And disjoint cycles are a special kind of cycle that we like to work with because they commute with each other. They have lots of nice properties there. However, there's another type of cycle which is also very useful to us. And it's the cycle of length 2, also known as a transposition. So, a cycle of length 2, that is of the form AB, is called a transposition. And the idea is that basically what a cycle of length 2 does is it just switches the A and the B. It sends A to B, it sends B to A, but it leaves everything else the same. So it just transposes two things. It's called a transpositions. And it turns out that any permutation can be described using just transpositions. Any rearranging of a finite number of objects can be done simply by exchanging two objects at a time repeatedly. Possibly many times, but just two at a time. This is somewhat intuitive when you think about it. If you actually imagine having a bunch of things in front of you and you're trying to order them from largest to smallest or something, well, you only have the two hands. And so what you will often do is just pick a couple up and put them down again, switch their positions over and over again in order to get the order to where it ought to be. Proving that the same thing is true in general here is not terribly difficult. So let's look at Theorem 51, which says that any permutation is a product of transpositions. Any permutation of a finite set is a product of transpositions. So first of all, note that we already have a theorem that says that any permutation is a product of cycles. Therefore, it's enough for us to show that any cycle can be written as a product of transpositions. Because then, if you want to write a permutation as a product of transpositions, you just write it as a product of cycles, and then write each one of those cycles as a product of transpositions, and then you're done. So let's let A1, A2, up through AN, I'll call it alpha, be a cycle. And we're going to write down its decomposition into transpositions very explicitly. So we claim that alpha is equal to A1AN, A1AN minus 1, A1AN minus 2, down to A1A3, A1A2. So we're going to claim that this is a way of describing the cycle A1 through AN as a product of transpositions. We're not making any claim about uniqueness here, and in fact, the decomposition of a permutation into transpositions is highly non-unique. We're just trying to show that it's possible to do it. All right, so we want to show that these two are equal. Well, how do we do this? Sorry. So let's let beta be the function on the right. And once again, we're going to show that alpha and beta are equal to each other by showing that they are equal on any input. So first of all, note that alpha of x equals beta of x for any x which isn't an AI. And that's because both alpha and beta only include AIs in the cycles making them up. And so if x isn't an AI, then neither alpha nor beta do anything to it. So now let's look at what happens to the AIs under alpha and under beta. Now we're going to handle a couple of things. We're going to handle this slightly differently for A1 and AN and for all the ones in between. So let's look at beta of A1. And let's look at what happens to A1 in this function beta. So first of all, A1 goes to A2. But then notice that A2 doesn't appear in any of the other cycles to the, any of the other transpositions to the left. A2 only appears once in this set of transpositions, and therefore beta of A1 is going to go to beta of A2 since A1, A2 is the only transposition including A2. Okay, so then let's look at what happens to beta of AN. Well, notice that beta of AN, or rather that AN doesn't appear in any of the transpositions except the leftmost one, except the last one. So that means that AN isn't going to change at all when you apply the first transposition to it, on the right, the second transposition to it, working all the way back. None of those are going to affect AN at all until you get to the leftmost one. So beta of AN is equal to A1 since A1 AN is the only transposition including AN. So that's good. That shows that beta is doing what it ought to do. It's doing what alpha does on A1 and AN. So now let's look at what happens to any of the A's that lie between those. So remember, we're saying that all of these are beta. So we're claiming. All right, so now let's let I be some number between 2 and n minus 1. And we want to look at what beta does. All right, so pardon me a second. All right, so then notice that two of the cycles in beta are, and these are right next to each other, these are going to be A1, AI, and then A1, AI plus 1. And that's because all the transpositions in beta start with A1, and then the second AIs are increasing, their index is increasing as we move from right to left. Furthermore, notice that AI does not appear to the right of these transpositions. So that means that under beta, we have that AI goes to A1 under this first transposition here. And then the very next transposition sends A1 to AI plus 1. Furthermore, AI plus 1 doesn't appear to the left. To the left of these. So that means that beta of AI sends AI to AI plus 1. Because as we move along, only one of the transpositions in beta include AI, and that'll send AI to A1, and then the very next transposition we apply will send A1 to AI plus 1, and then nothing else does anything to AI plus 1 again. So that shows that beta sends AI to AI plus 1. But that means that beta does exactly what alpha does. That means that beta of x equals alpha of x for all x. And so beta is equal to alpha. So this has shown that we can write any cycle as a product of transpositions, and therefore we can write any permutation as a product of transpositions. Now, as I mentioned, this decomposition into transpositions is highly non-unique. So let's take an example. Let's look at alpha, which is 1, 2, 5, 4, the cycle 1, 2, 5, 4. Well, it turns out that alpha can be written as 1, 4, 1, 5, 1, 2. This is actually just using the construction that we saw in the proof last time. We can always write a cycle in terms of transpositions by putting the first element first in all of them, and then writing the second elements sort of in reverse order from where they sat in the original cycle for alpha. But also, as it turns out, alpha is 4, 2, 2, 1, 2, 4, 2, 5, 1, 5. This shouldn't be obvious, but we can check our work. So if we look at what happens to 5, 1 goes to 5, and then 5 goes to 2, and then 2 goes to 4, nothing happens to 4, then 4 goes to 2. So that means at the end of the day, 1 goes to 2 as we trace through this whole sequence. And now, if we trace what happens to 2, nothing happens to 2 in the first cycle, then 2 goes to 5, then nothing, then nothing, then nothing. So 2 goes to 5. And now let's see what happens to 5. 5 goes to 1, nothing happens to 1, nothing happens to 1. 1 goes to 2, and 2 goes to 4. And then finally, we see what happens to 4. Nothing happens to 4 here, nothing happens to 4 here. 4 goes to 2, then 2 goes to 1, and nothing. So that means 4 goes to 1. So, let me just note where I got each of those. So that means that, oh, sorry, let me get those colors right. So alpha has two different ways of being written in transpositions, at least two different ways. Turns out that we can always get more ways of writing alpha as a product of transpositions. There are lots of different ways of writing it as a product of transpositions. However, what I want to look at is the number of transpositions that were used. So in the first example, we used 3 transpositions. The second example, we used 5 transpositions. And you can try a bunch of times to write alpha in terms of transpositions. One easy way of doing that would be to take a transposition decomposition you already have, and then just putting any transposition on there twice. And the reason why this works is because any transposition is its own inverse. Because if I take 2, 3, the order of the cycle 2, 3 is 2, which means that if you multiply it by itself, you get identity, which means it's its own inverse. So in particular, that means that 2, 3 times 2, 3 is just the identity. And so multiplying by the identity doesn't change anything. So we can get here another decomposition of alpha into a product of transpositions. And notice that this one has length 7. So here we have length 3, here we have length 5, here we have length 7, and this certainly isn't enough for a proof, but it might make you start to suspect that maybe there's something going on with the parity. Maybe it's the case that while alpha has lots of descriptions as a product of transpositions, the parity of the number of transpositions, that is, whether it's even or odd, maybe can't change too much. And it turns out that that's the case, and it turns out to be very important to us. So Theorem 52 says that for any permutation A, or alpha, I should say, the number of transpositions in a transposition decomposition alpha is either always even or always odd. Can't say how many there are, but for any permutation alpha, it will either, if you give it any decomposition in terms of transpositions, that is, write it as a product of transpositions, you will always get either an even number or always get an odd number. So let's look at the proof of this. We're going to start by looking at the identity transposition. So let's begin by showing that the identity transposition always decomposes into an even number of transpositions. All right, and we're going to do this by induction. So let's let the identity be equal to a product beta 1, beta 2, beta 3 up through beta r, where the beta i's are transpositions. And then we use induction on R. And basically what the induction is going to be is that R has to be even. So first of all, note that R is not equal to 1, and that's since a transposition is not identity. And then if R equals 2, that means that we're done. That means that we've shown, that means that the identity is written as a product of an even number of transpositions. So now let's assume that R is greater than 2, and we'll suppose that for any k less than R, if the identity is written as a product of k transpositions, then k is even. We're using a form of strong induction here. All right, so we're assuming here that R is greater than 2, and if we've got anything less than, if we can write E as a product of any number of things less than R, then that number of things has to be even. So let's consider the rightmost two transpositions, beta r minus 1, beta r. Actually, let's start a new page here. And let me write down, we've got the identity is beta 1, beta 2, up through beta r. So let's consider beta r minus 1, beta r. So this has to have one of the following four forms. So I'm going to use AB to represent the cycle BR, or beta R. And then on the left, there are some possibilities. It could be that beta r minus 1 is exactly AB. It could be that the previous cycle shares the first element A, but has a different element C. Could be that it shares the second element of beta r, but a different other element, or it could have two completely different ones. So these are basically broken up in terms of which elements do the two cycles beta r minus 1 and beta r have in common. And each one of these can be written in a different way. So AB times AB is just the identity, because as we mentioned before, any transposition is its own inverse. And then it turns out that the product AC times AB can be written as AB times BC. And you can check that these two just are the same. They have the same. They're the same function. BC times AB is the same thing as the product AC times BC. And then, I miswrote this last one. Sorry, that must have been confusing. CD times AB. And this one, we know that we can write this as AB times CD, and that's because these are two disjoint cycles. In particular, notice that this element A, which appeared in the right-hand term, has moved back. It appeared in the rightmost term BR. It's now moved back to be in the R minus first term. So now, let's consider the following. In the first case, we have that E is equal to beta 1, beta 2, up through beta R minus 2, and that's because beta R minus 1 times beta R is just the identity. So that means that R minus 2 is even by our inductive hypothesis. So we said in our inductive hypothesis that if you could write E as a product of any number of transpositions less than R, then that number had to be even. R minus 2 is less than R. That means R minus 2 is even by the inductive hypothesis. And that, of course, means that R itself is even. All right. Otherwise, we've moved the rightmost instance of A back one position. So it was in the very rightmost transposition, and if we replace the two transpositions on the right with the two transpositions given in the alternate form here, then we've moved the rightmost instance of A back one position. Now we can continue this looking now at the rightmost transposition involving A and the previous one and the previous transposition, and either every time we do this, we're going to have a product of transpositions that looks like one of these four. Every time we look at the transposition that has the rightmost instance of A showing up. And in each case, we either cancel those transpositions in the first, as in the first case, or we replace them with a new pair of transpositions in which the element A has moved backwards by one position. So either, as I said, canceling two transpositions or moving the first instance of A back, that is to the left. So we continue this. So the first instance of A was right at the rightmost term. We go through this process, then the first instance of A is one back from that, and then one back from that, one back from that, one back from that, and we keep going until either we get a cancellation or, well, what's the alternative? So we continue until we cancel, or until we cancel two transpositions, or until A appears in the leftmost transposition. That is, we'll have that the identity looks like some transposition involving A, and then beta 2, beta 3, up through some beta R. Where A doesn't appear in beta 2 up through beta R. But this can't happen. This can't happen since now this permutation AB times beta 2 up through beta R sends A to B, and thus isn't the identity. So that means that as we go through this process of looking at the rightmost position where A appears and then replacing things to move A back and back and back, at some point we have to have canceled rather than actually moved A back, because otherwise we would get to this position with some transposition involving A being the leftmost transposition, which doesn't work. Therefore, at some point, we must have canceled an AB, AB. So that means that we have that the identity is a product, again, of R minus 2 transpositions. And just like before, that means that R is even. Okay, so that was a lot of work, but we have now shown that if the identity is written as a product of transpositions, then that number of transpositions has to be even. It turns out now, though, that that we're just about done, because all the real difficult part was in working out just what happens with the identity. So we can finish up the rest of the problem for arbitrary permutations just in just a few lines. So now let alpha be a permutation, and let's let alpha equals alpha 1, alpha 2, up through alpha m, and beta 1, beta 2, up through beta n be transposition decompositions. Then we have the following. The identity is equal to alpha times alpha inverse. That's always going to be the case, which gives us alpha 1 through alpha m times beta 1 through beta n inverse. Now remember, when we take the inverse of a product, we have to reverse the order. However, we also know that the inverse of any transposition is itself. So we get the following. E is alpha times alpha inverse. We replace alpha with its transposition decomposition. Then we work out how the inverses go on that, and we get that alpha 1 through alpha m times beta n back through beta 1 is a transposition decomposition of the identity. And we just spent a lot of time proving that if that happens, then the number of transpositions in the decomposition of the identity has to be even. So that means that m plus n, which is the number of alphas and betas altogether, must be even. So m and n have the same parity. That is, they are either both even or both odd. So that was definitely more of a stretch, more of an exercise than some of the other ones that we've done so far. But it winds up being very important. It means that we can separate permutations, all permutations of finite sets, into two categories. They can either be written as a product of an even number of permutations, or they can be written as a product of an odd number of permutations. So this leads us to definition 53, which says that a permutation on a finite set is called even if it is the product of an even number of transpositions, and odd otherwise. That is, it's called even if it's a product of an even number of transpositions, and odd if it's the product of an odd number of transpositions. And what the theorem that we had before tells us is that this is well defined, that every permutation is either even or it's odd. It can never be both. So if you have some permutation and you have that it's written as a product of 1,726 transpositions, then you know it's an even permutation. That no matter how you write it down as a product of transpositions, it may have a lot of them, it may have only a few of them, but there will always be an odd number of them. So, in particular, we have the following definition. What we can do is we can look at the set of all even permutations and and look at the set of all odd permutations. But the set of all even permutations is interesting because of the following. The group of even permutations in Sn is called An, and it's also called the alternating group of degree n. Now, I've used the word group here advisedly. It turns out that if you look at only the even permutations of on a set of n elements, turns out that is a group, and that's another one of your exercises. And so it has an identity. Well, we've actually already shown that. So we already showed that the identity is an even permutation, because any description of it using transpositions has to have an even number of them. And so showing that it's closed under inverses and multiplication is not too difficult, but the AN is in fact a subgroup of Sn. Now, theorem 55 tells us about the order of AN. For any n greater than or equal to 2, the order of AN is equal to n factorial divided by 2. Now, you'll notice, or you'll remember, that n factorial is the order of Sn over 2. I won't go through the proof of this in detail, but I will mention what the strategy is here. So let's let An prime be all the things in Sn, but not in An, i.e. the odd permutations. And then what we want to do is we want to set up a function that goes from An to An prime, and it's going to take any permutation and send it to the permutation multiplied by the transposition 1, 2. And we know that this works because if alpha belongs to An, that means it's an even permutation. It can be written as a product of an even number of transpositions, which means if we multiply by one more transposition, that will give us an odd permutation. And therefore, this phi is well defined. And so we define this phi right here, and then show that phi is a bijection. Which means that the size of An, or the cardinality of An and the cardinality of An prime, are equal as sets. And therefore, since that means that 2 times the order of An is the order of, cardinality rather, is the cardinality of An plus the cardinality of An prime, which is the cardinality of Sn, which is n factorial, because these two sets make up all of the elements of Sn. So that's the basic idea. Is we show that there are exactly as many odd permutations as there are even permutations, and since every permutation falls into one of those categories, that means that the set of even permutations has to have an order exactly half of the order of all permutations. All right, so let's finish up with talking about how we can detect whether an element is in an or not. So we can use the following fact. A cycle is even, let me be more precise, an even permutation if and only if its length is odd. And the proof of this basically uses the same construction that we use to prove that every cycle can be written as a product of transpositions. If you compare the number of transpositions in the construction that we made with the number of elements in the original cycle, you'll see that they're off by 1, which means that one is even if and only if the other is odd. So a cycle is an even permutation if and only if its length is odd. So that means that, for example, the cycle 1, 2, 3, 4, 5 belongs to the alternating group of degree 5. And that's because this has length 5, so it has odd length, which means that it is an even permutation. And similarly, these cycle 1, 2, 3 belongs to A5, but the transposition 1, 2 does not belong to A5, and the cycle 1, 2, 3, 4 does not belong to A5. But what about something like this? What if we have a disjoint cycle decomposition of a permutation? 1, 2, and then 3, 4, 5. Well, so from here we can look at each one and we can see that this is an odd permutation because its length is even. Also, just because it is a single transposition itself, therefore it's a product of one transposition and one is odd. And then 3, 4, 5 is an even transposition. And then, an even permutation. Now, when working with a product of these cycles in a disjoint cycle decomposition, or even a non-disjoint cycle decomposition, then whether or not your result is odd or even follows the same rules as adding numbers. So this first one being odd means that this cycle can be written using an odd number of transpositions, and then this cycle can be written using an even number of transpositions, and therefore if you multiply them together, if you stick them together, that means that all together they make an odd number of transpositions, which means, again, they don't belong to A5. So the form of a permutation in terms of its cycle decomposition can tell you immediately whether that belongs to the alternating group or not. So as a more complex example, let's take 1, 2, 7, 3, 1, 2, 6, 4, 5, 3, 9, 7, 6, and 2, 6, 5. Now, this, of course, is not a disjoint cycle decomposition, but it is still a cycle decomposition, and we can identify for each one of these whether the cycle is odd or even. So the first one is odd because it's length 2. Second has length 3, which means that it's an even permutation. It's got odd length, which means it's an even permutation. Second one has length 5, which means it's an even permutation. Third one has length 5, which means it's even length 3 rather, so it's an even permutation. Last one has length 3, so it's an even permutation. So all together, this whole thing is an odd permutation. It can be written using an odd number of transpositions, which means in particular it doesn't belong to A9, which it looks like it sits inside. So this is how we can look at a permutation that's written in cycle form, even if it's not in disjoint cycle form, to tell whether it's an even or odd permutation. It turns out that the alternating groups are very important in a lot of places in algebra. In fact, as it turns out, the alternating groups are related to the existence of things like a quadratic formula. Now, we may not be able to get to it in this course, but you all know the quadratic formula. You may be familiar with the fact that there is a cubic formula that will give you the solutions to any cubic polynomial equation. There's also a quartic polynomial, a quartic formula rather, that gives you the roots of any quartic polynomial. But then when you get to degree 5, quintic polynomial, it turns out there isn't one. And it isn't even that we can't find, that we haven't found one yet. It's that we can actually prove that it doesn't exist. And in fact, it comes down to, via some very clever constructions and relations, it actually comes down to studying this group, the alternating group of degree 5. Turns out the existence of these formulas, the quadratic, the cubic, the quartic, is related to the alternating groups of degrees 2 and 3 and 4. But then you get to 5 and there's something different about the degree 5 alternating group to the previous ones. And so that's one of the reasons why these alternating groups are so important in the study of algebra.